And with no further announcements, I will introduce Ted Dahl, who's the treasurer of the White County Democratic Party, and he will introduce our keynote speaker.
All right, thank you, Richard. I'd like to welcome you all again. Wow, what a crowd, what a day. I'd like to thank Daniel and Rob and Jim for being our speakers today. Dr. Jim Smoot is our keynote speaker. He's going to speak on climate change and global climate science. Jim was head of NASA's Earth Science Office at Marshall Space Flight Center over in Huntsville. He's done numerous research projects, both using orbital satellites and airborne platforms. These include extreme weather, atmospheric processes, and ocean processes. He also served as NASA's representative to the Federal Interagency Task Force guiding national climate assessment process. He was selected as a member of the United States delegation. Good, I'm glad you turned out the lights. I thought the electricity had gone out there for a minute. Now if I could just read this, I'd be able to. He was also, assistant regional manager for the U.S. Geological Survey in Southeast U.S. and formerly a professor at the University of Tennessee. So I'm going to turn it over to Jim. Thank you, Jim.
Thank you very much, Ted. It's a pleasure to be here and see so many faces. I was asked to speak on climate change, and I thought I would speak a little bit about climate science as well as just climate change. And then hopefully at the end, some of my comments will take us. Oops, it's not on.
Speaking.
Oh, speak closer. All right, sorry. But anyway, at the end, hopefully I'll open the door to some follow-up discussion we'll have later this evening about what we do next, essentially. So go ahead, Ted, if you want to start. You know, when I tell people I was with NASA and did earth science, they're like, gosh, I had no idea.
Just step a little closer to the screen. There you go. Good. Thank you.
There you go. So people didn't understand that NASA did earth science. They said, no, we thought NASA just built rockets or something. And so I thought I would start, I think you want to back up one, Ted? And I wanted to put the mission statement for NASA so you could go backwards the other way. Yeah, there you go. Here's the mission statement. So you can see what NASA really is all about is driving advances in science, technology, aeronautics, on and on. And at the end there, stewardship of the Earth. I mean, that's right in the mission statement for NASA. This is what NASA does. So we do science, and we are all about the Earth. One thing you don't know, and go ahead to the next one, is the budget, okay? $19 billion is the overall budget. $5.6 billion goes to science, and of that, about $2 billion goes to earth science. Now, to put that number in perspective, that is about twice as big as the entire budget of the U.S. Geological Survey. So NASA does more earth science than any other organization on the planet. So it's not just a side thing that NASA does, it's a major activity of NASA. So I wanted you to have that perspective before we go on here. Go ahead, Ted. Now, what do we do in earth science? At NASA, we do all kinds of basic research. The section up there in the upper right is on flight. The way we do a lot of our work is from observation from space, and we also have high-altitude aircraft that we put instruments on and study from there as well. So flight is a huge part of how we do it. And applied sciences is a huge area for NASA where we develop applications that the real world can utilize. It's not just doing stuff for other scientists to appreciate, it's doing stuff for practitioners that can actually use it. So as an example, in my office in Huntsville, as an example, we developed 30 different applications that the Weather Service is using on a daily basis for their work. So we did all kinds of things, like I say, to put tools in other people's hands as well. And then, of course, bringing technology along as well. So developing new technology is another part about what NASA does. Okay, Ted. So just some of the missions that we currently have at NASA underway in earth science are given here. You might not be able to see them from the back of the room, but there's lots and lots of satellites that are up flying right now. And the way most of those operators are, they're polar orbiters. So if you can imagine it, they're going this way, the Earth is turning this way. So every day, those satellites see the entire planet and take measurements over the entire planet every day. So that's the kind of data that's collected by NASA. Go to the next one. And here's the ones that are currently being developed for future launch. So there's a bunch of new satellites that are coming on board to do new measurements and to also replace some of the existing measurements when the satellites basically serve their life and return to Earth, and we basically need to put a replacement up. Now, some of the kinds of measurements that we go, if you want to back up, can you back up one? Now, some of the measurements that I'll cover real quickly just so you get an idea. OCO is a carbon observatory. GPM is global precipitation measurements. JASON-2 is a radar altimeter. It's a couple of 100 miles up, and it is doing this polar orbiting, measuring sea level all over the oceans every day. It covers the entire planet every day, and it can measure sea level using radar altimetry to within millimeters from a couple of 100 miles up. Phenomenal technology. GRACE is one that uses its technology from a couple of 100 miles up and can measure essentially the mass of the oceans and so forth. So as it's flying over the oceans, it can tell changes in ocean levels based on the change in the mass. So I'll tell you about that a little bit more in a minute. But anyway, this is just a sampling of the kinds of stuff that NASA's doing that provides this data to the whole world. I mean, it's not just the US. We put this stuff out there on the web, and it's available for everybody to use these tools. Okay, go ahead. You can go to the next one. The International Space Station you might have heard of. Everything in yellow there is Earth science stuff that we have on the International Space Station. It's a platform that's about the size of a football field. This is a big platform with lots of instruments on it, and it flies around the globe constantly. It's flying at over 17,000 miles an hour and takes about 90 minutes to orbit the Earth. So it constantly is orbiting the Earth, collecting information and providing all that information back to scientists as well as to the public. Okay, go on. We also at NASA had airborne platforms where we could put instruments on high altitude aircraft, fly those in areas where we needed to study in detail. One good example would be the Global Hawk, which is an unmanned drone, very large drone with instruments. We would fly that over top of hurricanes and study basically what's happening inside hurricanes. We could loiter over top of hurricanes for like 30 hours with this thing before it had to return. Wow. So this is the kind of stuff that NASA does that you probably didn't have a clue that NASA was doing. Okay, you can go on. This is just a sampling of the current ongoing programs of scientific study with those with those airplanes, essentially. This isn't even the satellite stuff. This is just the stuff that we're doing with airplanes, with instruments, studying all kinds of processes on the planet. Okay, go ahead, Ted. The focus areas that I chose to show you that we do in earth science at NASA: carbon cycle and ecosystems, climate variability and change, which I'll talk a little bit more about, the composition of the atmosphere itself, water and energy cycles on the planet, the Earth's surface and its interior, as well as weather and extreme weather and things like tornadoes, things like that are things that NASA studies as well with our specialized tools. Okay? So let's talk about climate change, and I sort of like this cartoon, a little exaggeration here. The current rate of global warming, we should be able to swim over there and eat him in under 5 years. But that's probably a little bit of a stretch, but anyway, it starts the discussion. Go ahead, Ted. All right, the overview I wanted to start with is geologic time frame, if you will. So the Earth is something over 4.5 billion years old, and it has seen lots of significant climate change throughout its history. Natural causes of climate change include things like solar output variability. So what the sun gives to us varies over time, and at some points that makes a difference. I'll give you a clue, it hasn't recently, but anyway, in geologic terms it has. Orbital variation over time has also played a role. Volcanic activity, volcanoes throw lots of stuff into the atmosphere. That has played a role over geologic time. And then asteroid impacts. Some of those are pretty significant. The one that took out the dinosaurs like 66 million years ago was probably on the order of about 6 miles in diameter, moving at about 75,000 miles an hour. So it had a pretty good impact down around the Yucatan Peninsula area. Okay, now the human causes of climate change include the ones that you've heard about: greenhouse gases, primarily CO2, methane, nitrogen oxides, water vapor. Those are primary things that have caused the impacts, as well as deforestation and other land surface changes that humans have caused, as well as albedo changes. And this is basically reflections from clouds or soot and other particulate matter being deposited on snow and ice that absorbs heat rather than letting the ice and snow reflect that energy back to space. And then also urbanization, put in lots of black pavement and so forth that absorbs heat and so forth. So all of those types of things are human-induced changes to climate. Go ahead, Ted. If you look back, I call this paleoclimate, if you look back over time about the last 500 million years, that's a pretty good chunk of time. But remember, the planet's 4.5 billion years, so this is the more recent part of the geologic time frame. What you're seeing here, what's plotted here, is relative sea level, and this is generally the trend in sea level change. So over this geologic time, we've had hundreds of meters of change in sea level. That's a lot. So when I was young, getting into my professional career, at that time we thought of sea level as a datum from which we would measure things. We didn't think about it as a variable that was continually varying, but you can see it basically has varied a lot in geologic time. Now let's go a little bit more recent. If you look at the last 800,000 years, we actually have measurements of that period, and here's how we do that. In Greenland and Antarctica, we've been able to core down into the ice and be able to retrieve ice cores, take slices of that ice core and analyze it. And essentially, when that snow was packed down and the ice was formed, it trapped air bubbles, which were basically micro samples of what the atmosphere was at that time. And then we can analyze what's in those gases. We can get carbon dioxide as well as lots of other things from the gases in that ice. We can also look at the overall chemistry of the snow and understand what the atmosphere was like then. Isotopes are another, I won't get into the details of the chemistry of that, but those are the tools that we use to date it, so we know how old that ice was. We know when that was in contact with the atmosphere. And so with these tools, we can go back 800,000 years and recreate what the atmosphere was like chemically and physically for 800,000 years. So that's long before humans. Go to the next one.